So I'm here, welcome everybody. So I'm here to present this new feature of Circom. And I'm expecting that all of you know a little bit of Circom. Otherwise, it won't be easy to follow. But in any case, just to show that we are adding an important feature from the point of view of Circom as a programming language. Okay, so just a bit of context of what is Circom intended to help us in a zero-knowledge protocol. It's just this part that is in black, which is we have to build a circuit and be able to run this circuit. Okay, so this is where Circom help us. Okay, and so Circom is a DSL that has this special way of working, which is to explicitly provide the constraints of the circuit. Okay, so all is explicit, and then you can also provide an efficient way to compute the witness if you need, and in many cases this goes together. So you express the constraints and the computation at the same time, but in some cases it can be split in two parts. Okay, so another nice thing with Circom is that we have a library, a huge library with many circuits that we can use to build our new circuits on top of it. And this is encouraged because we can trust on these circuits, and then we build on top of this, and in many cases, we can get really safe circuits just because we build on top of things that we know are safe. Okay? So we have this nice ecosystem of tools and so on, but when writing circuits programs with Circom, we have a little bit, we are lacking types like in other languages. Okay, so because currently until yesterday, the only types you had in Circom were signals and arrays of signals. Okay, so of course you can do everything with that, but well, it's not the best way to work. Okay, so what I'm going to present here is that we will now be able to define new types, make collections of signals, and so on. So then what's the compiler doing? The compiler produces both things. The circuit, which is a constraint system in R1CS, and an executable in WebAssembly, currently in WebAssembly or C++, that can be used to run efficiently the circuit. Okay, so this is what the compiler produces out of the Circom code. Okay, so now let's motivate the problem. So this is just a piece of code from the library, from the baby jab circuit, and this is the other for this elliptic curve. And here you see that what we want to express is an addition. So 2 points added give a new point. Okay, but since we have no types, what we can do? So we have 4 inputs and 2 outputs that are just signals. Okay? Because of the names, maybe you can figure out what is the meaning. So the first 2 are the 1 point, the second are the other point, and so on. Okay, but nothing is really making this as each pair as a whole. Okay, as something that you know it goes together. Okay, so this what you can do, and then what happens? That you really want points, but you have signals, just signals. Okay, and even worse. In fact, they are signals, in this case, in the twisted Edwards form. Okay, so but they're just signals. Okay, so we are not seeing this anywhere, and it's not going to be checked in any place by the compiler. Okay, so we need, after this, we need better types. Okay, to structure the information, and then also to increase security, because if we add new types, then the compiler can check these types. Okay, and then we know that what we are passing is of the appropriate type. So this is what we pretend to do this. And here is what we get with buses. Okay, so buses are like structs in other languages, but we are programming circuits, so then we have buses, because bus is the name in a circuit. So from now on, we will use buses. And buses, the nice thing is that all can be mixed up from now on. So you can use you can define buses using signals, arrays of signals, and other buses, combine it with arrays of buses, whatever you like. So everything can be used in an orthogonal way. Okay, so the only thing that we don't have currently, but it will come, I hope, in few time, is recursion in the definition of buses, because we have to decide how to handle the null or something like this. Okay, so then buses define new types. Okay, and then type checking prevents from mixing different types. Okay, so the security is obtained like in other programming languages from now on. Okay, since you have types, so the compiler will type check everything, and you will avoid maybe using signals that have not a real meaning you expect. Okay, so this is the point. And then very soon we will release a new version of the Circom library, which is the circomlib, using all these buses and change completely. I will talk about this a bit later. So what we believe is that a complex Circom program in production, and we have seen many projects that use Circom in the introduction, so must use these buses to increase readability, because if you want to audit your circuit, buses will help a lot, and also to increase security. Okay, so let's do a little bit of practice with this. So the very easy example. Okay, so suppose that you want to compare days or whatever, then we have the problem as before. Okay, and then you can use names of the signals to help a little bit, but this is not much. Okay? Later you can say, well, no, let's put it all together because then it will be clearer. But I'm not sure this is clearer than before. Because now, what's the day? The 0 or the 1 position, okay? You don't know, and it's impossible to know, okay? So it makes not much sense to do it like this. Okay, so what can we do? So, of course, use a bus, use a struct. Okay, then you define it like this, and from now on, you can now define templates, you see, using this, like before we had signals. Okay, so it's simply as simple as this. Okay, note one little difference. So there is just a tiny difference. Before, it was the input and the output keywords were in the middle. And that is quite ugly with buses. So we decided to change a little bit the syntax, and from now on, the recommended syntax is to put the input word keyword and output keywords first, and then the type, and then the name. Okay, but the old style will be still valid. It will compile and no problem. Okay, but just take this into account. It's nicer if it is written like this. Okay, let's go a little bit further. What can we do with buses? Not only this simple thing. We can now have parameterized buses like we have parameterized templates. Okay, so this parameter is something that will be known at compile time. And exactly the same you have for templates, you will have it for buses. And then here, what we do is just we define this array of dates using this parameter. And the nice point is that then everything fits well with the templates, because, for instance, here I can define a template with a parameter n that uses an input uses the same parameter, and then everything will work well with the sizes of things and so on. Okay? And then, of course, then you can call another template with the same n, but then I pass the field of the array of dates, and everything matches the types, and everything compiles. Okay? In general, I would say that clearly this looks nicer and it's far more readable. Okay? Otherwise, there will be all this amount of signals around, all mixed. You have to choose whether you have arrays of arrays or many arrays. So it's just much cleaner and easy to read. Okay, now we go a step further and we mix buses and tags. Tags is something we introduced kind of 2 years ago. And we were having a bit of subtyping with tags, and now we'll have types and subtypes. This is what I want to present here with this mix of buses and tags. So the point is this, that tags provide a simple form of subtyping. Okay? We don't have inheritance and things like this, but we get a little bit of subtyping with tags. But now it's really far more powerful combined with buses. Because now we have types, and then we can just get a little bit of subtyping with tags. And then what happens is that we create new types with buses, and we define subtype relations using tags. Okay, so you see here that then when you define a bus or use a bus, so tags can be inside and outside, and with different meanings. If you have it inside, they somehow are restricting every instance of this bus. I'm saying that this field has this property. Okay, so I'm restricting what should be in the bus. And if I add it outside when using the bus, then I'm restricting the particular instance of the bus. Okay, so I can do it both. I can define something that I always want to have this property in a field. I add the tag inside the bus. But if it's something that maybe sometimes I need it and sometimes I don't, then I add it outside when using it. Okay? So the point is somehow that before we were only with tag with signals, we were only able to express tags properties of a single signal. Now, since we can put a tag on a whole bus, we can express properties of a combination of signals. Okay? So it's much nicer in this sense. And later on, if you add verification techniques and so on, it will go much better because we can check the semantics of a whole bunch of signals that go together. Okay, so let's see it in the example of this and going a bit further than this. So this is what I mean by tags inside. Okay, so I here say, for instance, don't be much worried about the semantics of these tags and why I'm using max bit for day, and just to show that you can use different tags and as many as you like, none, one, two, different things for different signals, okay, whatever you like. Okay, so this is just meaning that there is some bound restriction on the signals you can get there. Okay? So there is one thing. But then suppose I create this bus, which is profile for an ID, and then for a bunch of dates, meaning whatever. And then what I want to add for dates is that this is a valid date. Okay? So then I add this tag saying this is a valid date. And what's that? So I can have a template that creates a valid date from, and what's the meaning of creating a valid date? It means adding constraints that ensure that the date is valid. Okay? We are creating circuits that ensure things. Okay? So we can do that. And look, if I do the template without any assumption on the input signals, then I add here constraints and so on, checking all the properties. The properties of the day, the month, and then also the global properties of if the month is this one is January, then it should be between 1 and 31. If it's blah, blah, blah. Okay? But the difference between the input and output and the fact that whether I already know some property or not. Suppose that because this is used in some context, I already know all these tags from outside. Then if I know that it should be like this, then I have it in my circuit, and I don't need to recheck it again. You know, if you have built circuits many times, since you're not sure whether you know or you know something or not, you keep adding the same constraints again and again and again. So using types and subtypes by means of tags, we avoid a lot of recheckings of things, and which end up with a better and more efficient circuit. Okay, so now, what's the impact of all that in the circomlib? So, well, huge. Okay? But I will just show a little bit. So what we are doing in this one while writing is adding buses and tags everywhere, or in many places, and also making it compatible with different primes. Remember that initially we only have this BN prime, and then circomlib was intended to be used with this prime. But now we have kind of, I don't remember, maybe 6 more primes or even more. And then what happens with the circomlib is not adapted to this. So we are just ensuring all the circuits that we can being compatible with every prime. Okay, so of course you will use which prime are you exactly using and so on, but you can make it. And this will be a nice improvement. So the nice thing is that we have added these buses and tags, and still we have been able to prove and formally prove that in most cases the number of constraints remains the same. Well, when using minus 01. Okay. By the way, which is now the default. Until now, the default was 02, but from this release on, the default is 01, because many people is using Circom for Plonk, and then 02 is not the way to go. Okay, so from now on, this is the default. Okay, so keep it in mind, because it's important. And of course, looking at the new circomlib will help to understand and get ideas about how to use and where to use this. So let's show a simple example of the one single example of this use. Okay, so let's come back to this baby jab elliptic curve. So you have the others and so on for the twisted Edwards form. Okay, look there, point. It's just like this. You have 4 inputs and 2 outputs, no meaning apart from X, Y used in the name. And then you have the version, the Montgomery, the others for the Montgomery form, and all of a sudden, now it's no longer 2 signals, but an array of dimension 2. Okay, so as the creator, I was not there. So, and you have this, okay? So, for instance, this difference. But even more, if then you look at the conversion from Edwards to Montgomery and back. So here you see, you have even this kind of, well, it's not a type inconsistency, but inconsistency, but you have there to express the point with 2 signals, and here's the array of dimension 2. Okay, but it's all the same because I have 2 signals. Okay, but it's not helping to read, and also it's clearly error prone because you can mix things that you don't want to mix. Okay, so let's do it with buses, which is far more natural. Then I have a type for Edwards point. Okay, so 2 fields, and that's it. And then, oh, what a nice thing. Okay, you see? This P1 point, Edwards point, P2, Edwards point. Oh, now I go to the Montgomery form, another bus. Okay, so Montgomery point. Then, oof, nice again. You look, it's clearly different. Okay, and you will never mix both because you cannot pass one type to the other because the compiler would say no, would say type error. Okay, and now look, it matches perfectly. You get a converter that takes an Edwards point and produces a Montgomery point. Okay, and same reverse. Okay, so now it's readable, and thanks to the type check, you have type safety. Okay, so it's clearly more reliable. Of course, it's far more readable and more reliable. Okay? You understand a bit more what you're doing. But now let's do this with tags. Then the point is this subtyping. So because we've seen that they're all points. So should we have these 2 points? Well, a proposal is, no, use only points. And then use tags to distinguish them. So here, you see, you have points, and then you add the tag Edwards. And in the other way, we don't add a new boss, but we use the same, but we add the tag Montgomery. Okay? Now you cannot mix them again, because you will check whether you have the tag and you or not. And of course, except if you, for some reason, decide to add yourself 2 tags, which you, I mean, still it's possible to make mistakes like in other languages, but on purpose, you have to define a type for something that you really don't know if it is fulfilling the properties or not. Okay, so there is the kind of things that will be prevented thanks to types in this context. Okay, so then what we have is this, and this, and then when you have the conversions, everything matches again, because here I will get this Edwards point, then I get an output point with the Montgomery tag that I will be able to use there in the other because it has the tag. Okay, everything matches types, and it works nicely. Okay, of course, all this is checked by the compiler in the type check, and it has no impact at all in the amount of constraints and so. Okay, if you need to add some extra constraints because you need to be sure that the conditions that you have associated to the type are met, then you add constraints. Okay, but there is what you should do. It cannot be that you assume that something fulfills a property, but you don't add constraints, because then, of course, maybe what you produce with the Windows will fulfill it, but someone can send you a proof that is not fulfilling this, and you will just say, okay, good. So then, with tags and buses, we get readability, type safety, but also we are far more reusable with the code, because maybe we have operations for points that are always the same, and we can reuse it in both cases. Okay, so it's just the standard situation with subtyping. Okay, it simply helps in reusability. So finally, what we have in this, as I said, in this new Circom, we have added these buses, tags, and make it compatible. And the nice thing is that what we pretend is that if someone builds circuits on top of the circuits from the Circom lib can be in the safe side, in the sense that we can even certify that if you only use the templates of the Circom lib to create new buses or to add tags and so on, then you are sure that the properties are fulfilled. And you're using properly the baby jab elliptic curve and so on. Okay? So it's these kind of things. You're not making mistakes in this sense. You're using things properly, and you can trust all this. Okay? So you are safe just by default because you're building on something safe. So we'll, later in the future, we will really give a precise definition of this. But this is what we intend to do, to have circuits that are safe by construction. Okay? And, well, we are still improving and extending it, so it will be ready very soon, but it's not yet. So conclusions. So Circom is really one of the most widely used languages for zero-knowledge protocols. As I said, many of the projects that were shown in the intro are built using Circom. And, but until now, we're missing these extra types or this type system, a proper type system in the language. And this is what we are providing with in this new release. Okay, these buses that provide us the way to structure circuits. It provides a far more convenient type system, and then we can ensure this type safety. And also, we believe that it will help auditing ZK projects. And the new Circom lib will take advantage of all this. Thank you.
Thank you very much, Albert. Do we have any questions? Oh, great.
Yeah, so at one point you said that circomlib 2 was using some kind of formal verification. What exactly did you use, and how did you do it?
Well, I said what I said is that what we have formally verified. I mean, you know, there are circuits made of many, sometimes thousands of constraints even for the circomlib, for just a simple part, just using one of these circuits in the circomlib. Okay, so then, imagine that you want to check that introducing all these, you are not having an overhead in the number of constraints. Okay, so you want to check, and also you want to check that you are saying the same, because the circomlib was already audited. Okay, so imagine if we just don't know if they are the same after changing, we need to audit again. So what we have verified for most of them, and the ones that they don't fulfill the property of being exactly the same as before, is because we already know that we have added some extra constraints, okay? Because we know it in purpose. Or we have removed some constraints because of the tags. We know that this was already checked, so then we don't need to add them. But apart from these situations, we have proved that the circuits before and now are the same, but simply are defined and described in a much better way. Okay, more readable, and also nicer in the sense that you can use them in a safe way. Okay, so this is the key point. So this is what we have verified.
I think we have time for one more question.
Could you perhaps compare and contrast what sorts of things can go in buses and what kinds of things can go in templates? For example,
sorry, in buses?
Is it possible to put something like a constraint or a witness generation procedure inside of a bus, such that all instances of the bus have that, or not?
No, so that would, okay, nice question. So thank you. So there is the point where we have code inside the bus and is producing constraints. So we are not allowing any code inside the bus by now, but probably we will. But only to the final, so for instance, if you want to have this recursion, it would be good to have, using the parameter, deciding whether some field is there or not. And then you can have a nice form of, because the notion of null in a circuit is not easy. Okay, so it's a weird, it has a weird semantics. But if you can add code, you can have a conditional saying, well, if n is 0, then you don't have this field. Okay, for instance. And then you can probably add some code this way. I don't think we will like to add code in the sense that if you have some bus, it will just directly introduce a set of constraints. We are not planning to have this.
Great. Thank you very much. Let's thank our speaker once again.